morning friends, let's today get into the techniques of evaluating improper integrals. We have learned the principles of beta, gamma and Laplace techniques of evaluating improper integrals. Today I would like to take you on a small tour of examples where we can see all these things being used under different situations. My first example is an improper integral which appears like this. Well, you all can see that the log sin x function is not defined at the lower limit x is equal to 0. Therefore, we can call it an improper integral. So how do we go about this one? We don't need the knowledge of gamma or beta functions, but we can use basic level mathematics in order to evaluate this. Remember, if you can call this integral as I, we can use the property I is equal to 0 to pi by 2 log sine pi by 2 minus x dx. These two integrals are equivalent. So this can be reduced to a new integral which looks like this. Now, evaluation of log sin x is equivalent to evaluation of log cos x, but because both are tough integrals, we can take their sum 2i 0 to pi by 2 log sin x cos x dx. It may appear that this is a much more complicated integral, but you can see that we can reduce like that and break it like that. Now, once you have done this, this integral can be proved to be equal to I itself. So 2i is equal to I minus pi by 2 into x from 0 to pi by 2. What I mean is 0 to pi by 2 log sine 2x can be reduced to I itself by a simple substitution for 2x. If you can do that, this will be equal to the given integral itself. So 2i minus I is I, which is minus pi by 2 log 2, or we can also write this as I is equal to pi by 2 log half. So either we can produce this as the final answer. So this is how, using basic intermediate techniques, we can solve a problem like this. Well, my second example will be similar with a little bit more complication. The problem is to evaluate integral 0 to pi x log sin x dx. Again, this is an improper integral because log sin x is undefined at the lower limit x is equal to 0. We'll adopt the same procedure, call this as I, and create an equivalent integral I is equal to 0 to pi minus x log sine pi minus x dx. Reduce this and you'll have 0 to pi minus x log sine x dx. Now this is the original integral, this is the transformed integral. As usual, we'll take the sum of these two and you will get, after cancellation, pi log sin x dx. Pi being a constant can be taken out and you'll have 2y is equal to pi 0 to pi log sin x dx. And all of us know in the range 0 to pi, log sin x dx can be written as twice integral 0 to pi by 2 log sin x dx. This is a well-known property. And the value of this integral 0 to pi by 2 log sin x, if you refer to the previous example, is equal to minus pi by 2 log 2. So with this, we get I is equal to minus pi square by 2 log 2. So this is how, once again using elementary integration techniques, without the knowledge of gamma or beta functions, a few problems can be solved. Now the third example that I am taking up is a problem that is generally considered very hard to solve under normal integration techniques. Now this particular function can be done by a couple of methods, of which I am going to take up one of them. In this problem, we have an improper integral 0 to infinity e power minus x square dx. So e power minus x square dx is definitely a decaying function, but exact methods do not exist. So we'll have to either go towards special functions like gamma or beta, or we go towards Laplace transform. Both approaches are available. Let us say we want to do it by the Laplace transform approach. So what you do is you simply require a substitution. Let us introduce x square is equal to t as a substitution, that is for this. So 2x dx is dt. So dx will be dt by twice square root of t. So if you can introduce it here, you will get half integral 0 to infinity e power minus t by square root of t dt, which we can write as integral 0 to infinity t power minus half e power minus t dt. Now if you look at this one, we can either do by Laplace, or we can also use a gamma definition. Suppose we want to use a gamma definition, then this is nothing but half gamma half, because t power minus half can be written as t power half minus 1, and going by the definition of the gamma function, this is nothing but gamma half. All of us know gamma half is square root of pi, so therefore square root of pi by 2. This is the option for this particular problem. Option number C happens to be the correct option. However, suppose somebody wants to approach this problem using the Laplace transform. How does he do it? So he will take off from this point, because it is at this stage we have two options, the gamma option or the Laplace option. If it's the Laplace option, then this looks like integral f of t e power minus st. So the choice of s will be 1, but we need to find the Laplace transform of t power minus half. So what we do is we write it as Laplace transform of t power minus half evaluated at s is equal to 1. So the Laplace transform of t power minus half is gamma minus half plus 1 by s to the power of minus half plus 1, right? Because the Laplace transform of t power n for fractional powers is gamma n plus 1 by s to the power of n plus 1. So if that is the case, this is gamma half, so it is square root of pi divided by s to the power of half. And let us not forget there is already a 1 by 2 here, so I have to multiply with 1 by 2. As we have said, the substitution is s is equal to 1. So at s is equal to 1, this reduces to root pi by 2 into 1. So you can see that we get the same result whether we come through the gamma function or we come through the Laplace transform approach. So if the student is good in all these techniques, then he'll have a couple of options before him by which he will be able to approach the problem. So confidence levels will grow if you are good at your fundamental levels, and you must believe in tremendous practice, because once you are equipped with so many techniques, you are empowered to approach the problem confidently. We will be seeing some more examples based on these techniques in the next couple of minutes. Okay friends, now my selection of the problem will be possible by two techniques, but I am going to show you the Laplace approach. There is a much more tougher technique available, but that is not suitable for an examination like GATE, because this exam is all about managing time. So the second technique I am not showing you. However, for those interested students, this method is based on the Leibniz technique of differentiating under the integral sign. I am not going into that because it's too heavily loaded and cannot definitely be done in a couple of minutes. So my choice for this problem is going to be the Laplace transform. So let's see what that question is. Well, this is a classic example of an improper integral, but which can be approached by Laplace transform. So we will call this a division by x problem. So the technique is, you take the numerator, find the Laplace transform of that, and then division by x means the process of integration is involved. So let me take you step by step how to approach this problem. So let us call f of x is equal to e power minus ax minus e power minus bx, the numerator. So you find the Laplace transform of this function. Now these are basic functions whose Laplace transforms are known to all of you. So therefore, let's get this. Call it f of s. Now when you divide with x, then an integration is involved. The limits of integration are s to infinity, 1 by s plus a minus 1 by s plus b ds. So this is a fairly simple integration to perform. Log of s plus a minus log of s plus b. Simplification, log of s plus a by s plus b from s to infinity. Well, you can manage these substitutions, you have to be careful, but you will ultimately get log of s plus b by s plus a. But that is not the real output, right? S is a variable that enters whenever you take the Laplace transform. In this context, you must know what is the value of s that you have to substitute. So I will give you a very simple technique which you can remember for all the problems. The technique is integral 0 to infinity f of x dx will be identically equal to the Laplace transform of f of x, in which you can substitute s is equal to 0. So this can be remembered as a standard technique of evaluating indefinite integrals within the limit 0 to infinity using the Laplace transform technique. However, one must be careful to know that this technique will work only when the Laplace transform of f of x exists. And remember, the Laplace transform of f of x is always a function of s, where s is a real or a complex variable. So you just need to substitute s is equal to 0. Now let's come back to this problem. We have seen that the Laplace transform of this has been found, and there's a division by s, so we applied some integral property, and we got the final output. So you just need to put s is equal to 0 and you will get log b by a as the option, and that appears to be option D in this case. So please friends, remember, Laplace transform is a very powerful tool. If you know the properties, then you can solve very complicated improper integrals, but mind you, the limits must be 0 to infinity. So the fifth example that I am selecting, let us see how to pick up the technique. The problem is, first let us see whether this is an improper integral or not. Remember, there are three kinds of improper integrals: a type 1, type 2 and a type 3 improper integral. Type 1 improper integrals require a minus infinity or a plus infinity in the limits. Type 2, whenever there are singularities in the given range. And type 3 is an improper integral where you have a blend of both these things. This is a type 2 improper integral because in the range 0 to 1, log of 1 by x is not defined. So therefore, this is a type 2 improper integral. So what options do we have before us? Definitely not a straightforward integration problem. You will have to introduce substitutions. So the substitution that we are going to make will take you towards a beta or a gamma function. Does not matter whether it gets reduced to beta or gamma, because beta can always be converted into gamma. So I will introduce log 1 by x as t. This is my substitution. Well, you can easily see that 1 by x is equal to e power t, or x is equal to e power minus t. So all the basic things must be followed, and apart from this, we'll have to change the limits of integration. Let's pick the lower limit, put x is equal to 0 here. Log 1 by 0 is undefined. Suppose you call it infinity, then t is infinity for this lower limit. So in the transformed integral, you will have an infinity at the lower limit, and when you take x is equal to 1, log 1 is 0. So that's the corresponding upper limit. So if you bring in these changes now, you get minus e power minus t dt by square root of t. Let us look at this. Absorb this minus sign, interchange the limits, and then you'll have 0 to infinity t power minus half e power minus t dt. Now you have already seen this integral just a few minutes back. This is nothing but gamma half. So let me not waste time, call this gamma half, and therefore the output is root pi. The correct option is B. Let's go to the sixth example, an improper integral. 0 to infinity x to the power of 7 by 7 power x dx. Well, we can set it very nicely, something like this. A power x is equal to e power x log a. I hope all of you know this very fundamental conversion of exponential functions. Exponential functions need not necessarily be of the e power x or e power ax format. Any a power x can be called an exponential function, but having the base e has got several advantages in calculus. So if you can write a power x like this, 7 power x can be converted like that. So we can write 0 to infinity e power minus x log 7 into x to the power of 7 dx. So this being the case, let's pick up this term and make a substitution. X log 7 is equal to t. So x is equal to t by log 7 dx is equal to dt by log 7. This is straightforward. So let us now bring in these changes. Replace x log 7 with t, replace x with t by log 7, replace dx with this, and see what is going to come. No change in limits. So we'll have e power minus t by log 7 whole power 7 dt by log 7. So we can write this as 1 by log 7 to the power of 8 integral 0 to infinity. T power 7 can be written as t power 8 minus 1 e power minus t dt. I hope you all have recognized this is a gamma integral. So this is nothing but gamma 8 by log 7 to the power of 8. Now gamma 8 is nothing but 7 factorial. 7 factorial by log 7 to the power of 8. So you can see clearly option 1 will be the correct option for this particular problem. So when you start, the problem may look tough, but use proper substitutions, remember the principles, and you find that it's all within gamma, beta and Laplace. So that's how you must approach. Okay friends, the next problem. I hope all of you can easily solve this. Again, there are two possibilities, the Laplace possibility and the gamma integral property. I think we'll go for the easiest one, which is the gamma option. So write this as x to the power of 3 by 2 minus 1 e power minus x dx. So this is plain gamma 3 by 2. Gamma 3 by 2 may be directly remembered or you can derive. If you want to derive, write this as gamma half plus 1. And you know there's a recurrence relation. What is that? Gamma n plus 1 is equal to n into gamma n. So if you can use that property for this problem with n is equal to half, you will get half gamma half. Gamma half is square root of pi. So this happens to be the output, and the option is B. Option B is the correct option for this problem. No complication, straight gamma detection is sufficient. Question number 8 is a very nice problem which looks harmless, but again requires some substitution so that it can be solved by the beta integral. The problem that we have selected is integral 0 to 1 minus x cube to the power of half. So what we do is we make a trigonometric substitution. X cube is equal to sine square theta. So 1 minus x cube reduces to cos square theta, right? So this becomes cos square theta. X can be written as sine theta to the power of 2 by 3, and dx is 2 by 3 sine theta power minus 1 by 3 into cos theta d theta. So you may get a temporary feeling that the problem is going out of control, but let us not forget that there is one form of beta integral which involves sines and cosines. So the plan is to route the problem through the beta integral. and the limits of integration, as you can easily see, become 0 to pi by 2. I don't think we have to go into that detail. So 0 to pi by 2 cos square theta power half. Then you attach this 2 by 3 sin theta power minus 1 by 3 cos theta d theta. Right? Let's do a little bit of simplification. 2 by 3, 0 pi by 2. This becomes cos theta. There is already another cos theta, so it becomes cos square theta. So we have sin theta power minus 1 by 3 cos square theta d theta. Now you must be able to handle this integral. Remember, the beauty of special functions is that ultimately no integration is done, but there are standard templates by which we can read the answer. So this form takes you towards a beta integral. So let me write it here and tell you how we can convert it into a beta integral. So this is 2 by 3 into half beta minus 1 by 3 plus 1 by 2. So if you can call this as P and this as Q, then we will get half beta P plus 1 by 2 Q plus 1 by 2. So this becomes 2 by 3 by 2. So it becomes 1 by 3, 1 by 3 beta 1 by 3, 3 by 2. Well, it is difficult to continue beyond this. I hope we can stop it here and we'll find the correct option is A. The next question that I'm going to take you can be solved by the Laplace transform method. The question is integral 0 to infinity t into e power minus 4t sin t dt. Within Laplace transforms, there are two possible approaches, and I will take you to the easiest one. So what you do is begin with finding the Laplace transform of sin t, then you find the Laplace transform of t sin t, and then finally use a substitution to produce the output. A slightly advanced technique will involve finding the Laplace transform of this product. That will take a little bit more time because it involves a shifting property. So I would not like to solve this problem that way, but make it extremely simple. So how do we proceed? Begin with the Laplace transform of sin t. All of us know this is available in tables. Let us call this f of s. Then the Laplace transform of t sin t is minus f dash s, one of the properties, and this will be 2s by s square plus 1 whole squared. Let us call this g of s. Right? Now what is that which produces the answer? The answer will be g of s evaluated at s is equal to 4. So you need to just substitute s is equal to 4 in the gs, and you will get 8 by 16 plus 1 whole squared, which is 8 by 289, and the correct option is B for this problem. Okay friends, let's look at the 10th problem. So the process is begin with the transform of sin t, then use the property of finding transform of t cube sin t, right? So the Laplace of sin t is 1 by s square plus 1, call it f of s. Laplace of t cube sin t is minus f triple dashes. So we need to differentiate this function 3 times with a minus sign and then finally make a substitution for s so that we get the final output. So let me show the detailed differentiation of this function. Let us begin with f dashes. This is a straightforward differentiation and you will get minus 2s by s square plus 1 whole squared, right? Because the derivative of 1 by s square plus 1 is minus 1 by s square plus 1 whole squared into the differentiation of s square plus 1, which is 2s. Now let's go to f double dash x to differentiate this one. So it will be minus 2 into s square plus 1 whole squared minus 2s into s square plus 1 into 2s by s square plus 1 to the power of 4. So that makes it, I think an additional 2 is also required. So we will get an additional 2 because the differentiation of s square plus 1 whole squared is twice s square plus 1. Now let us pull out one s square plus 1 and reduce this. So you will have minus 2 into s square plus 1 minus 8s squared by s square plus 1 whole cube. We will reduce this and also absorb the minus sign. So 2s square minus 8s squared with this minus sign will make it 6x squared minus 2 by s square plus 1 whole cube. So this is f double dashes. What is that we require? We require f triple dashes. So I'm going to differentiate this once again. F triple dashes is equal to 12s into s square plus 1 whole cube minus 6s square minus 2 into 3 times s square plus 1 whole squared into 2s divided by s square plus 1 to the power of 6. With this, the differentiation part is over. However, remember there is a small substitution we have to make finally. So we'll slightly reduce this before we substitute. What can be done? S square plus 1 whole square can be taken out common from the numerator and we can cancel out here. So we are left with 12s into s square plus 1 minus, this is gone, we'll have 6s into this quantity, 6s into 6s square minus 2 by s square plus 1 to the power of 4. Well, whether we should simplify this or not is left to the student, but what is that we want? We want the answer through a substitution. For the answer, come back to the main question and look at this exponential function. So the coefficient of t here is minus 1, so we have to just pick up s is equal to 1 and substitute there. So put s is equal to 1. So we will have integral 0 to infinity t cube e power minus t sin t dt is equal to, remember this is where the answer is produced, minus f triple dashes with s is equal to 1. So I'll write that clearly for you, minus f triple dashes at s is equal to 1. So I'm going to use that, put s is equal to 1 and don't forget we must attach a minus sign. So we will have minus, put s is equal to 1. So this becomes 2 into 12, 24 minus, this is 6 into 6 minus 2 is 4 by 2 to the power of 4. 24 minus 24 is 0. And the correct option is C. So this can be a challenging problem for many students, and you will be lost if